Alright, hello everybody, my name is Petr Zemek, also known as Servats, and in this screencast I would like to go over Python's object model. The screencast is based on a talk that I had a few days ago, and I thought it would be nice to have a recording of this talk where I go over all the examples. I don't have to rush through them, and I can post them. I can post the screencast on YouTube. So here we go. Before we begin, as I said, it's going to be a screencast, a live demo accompanied by various examples. Here is a link to these examples. So if you go there, you can download the examples, play with them. I will try to describe all of them during the screencast. But if you want, you can experiment with them afterwards. And also a disclaimer, in what follows, if I say Python, I mean Python 3.6 or newer. While most of the things that I will tell you are valid for all Python 3 versions, there are some constructs that are only available since Python in Python 3.6. So this is why I have the disclaimer here. But 99% of what I say should work in any Python 3 version. Do not even try to use the knowledge in Python 2, as it won't work. Python 2 is a different beast, and I don't want to get into that. So Python means Python 3. So let's get started. What is an object? An object can be described as an abstraction for data or real-world objects. In object-oriented programming, you put both data and functions that manipulate these data into objects. So instead of creating structures and functions which are independent, like in C, in object-oriented languages, you put data and functions that manipulate these data into objects, so they are encapsulated there and can be passed together. So this is what we mean by an object. And what is an object model? For a programming language, it is essentially the characteristics of objects in that language. For example, are there classes or just objects? For example, in Python, we have classes, or in C++ or Java, but there are languages oriented towards prototypes like JavaScript, where you don't have classes, and if you do, they are just syntactic sugar over objects delegation prototypes. Or it can mean, it can answer the question whether there is multiple inheritance or not. So for example, in Java, you have single inheritance, but in C++ or in Python, you have multiple inheritance. Or it tells you how are objects constructed or destructed, how do you access attributes, and also if those characteristics are ad hoc or they have a theoretical foundation. So that's an object model. So how do you work with objects in that particular language? Let's move to the basics. I have made an example here. I will just skim through it. I expect all the viewers to know the basics of Python. I will not describe what is a class, what is a method, what is a property. So you should know that. If not, I suggest reading something about it before continuing in the screencast. So here we have an import statement, base class. I will tell you more about the 3 dots. Here we inherit from geometric objects to create a circle. So here is a docstring, a documentation string for that class. Here we have an init method. Here's a method for computing the area of the circle. Here is a property that returns us the diameter of the circle, and a class method which can be used to create a so-called unit circle, which is a circle having radius 1. Here we instantiate circle, and we can access its radius, compute its area, or access its diameter via the property. We can create another circle, and as we can verify, its radius is 1. So that's the basics. I will not go over through them. I expect every viewer or listener to know this. The one thing I like about Python is very little is truly magical. The language goes almost superhuman lengths to expose what you might need in the language, so it's not hardwired into the interpreter, but you can change it, use it, understand it, and as we will see, almost everything you would like to do, it's possible in Python. There are some costs, for example, performance suffers by this, but if you care about performance, you probably already use other languages. So that's that. First thing, in Python, almost everything is an object. So let's bring an interpreter and let's take a look at some examples. So for example, if I instantiate an integer, I can call methods on it. For example, bit length tells me how many bits do I need to store this integer. So if I have this 260, I need 9 bits to represent this number. Also, I can use this object, the ellipsis, as a filler or as a placeholder for code that is supposed to be written. So that's the beauty of Python. It almost looks like an executable pseudocode in which you can use 3 dots. And also it has its methods and attributes. Then if I create a function, I can put a docstring in there, and I can access this docstring afterwards, which can be useful for documentation tools to automatically extract documentation, or you can even modify the docstring. So for example, you can automatically grab docstrings from base classes and put them into subclasses. So you don't have to duplicate your documentation strings. And also we can take a look at code objects. So every function has its code, and we can disassembly this bytecode by using the this module. So here it says that I just load none and return that. I won't talk about bytecode. That's for a whole nother topic. But bear in mind that you can even access bytecode and create bytecode, custom bytecode in Python. So almost everything is an object. The other thing is that everything actually inherits from a class named object. So if we take a look at the base classes of int, it's an object. If we take a look at dict, it's also an object. So if you create your own class and take a look at bases, there's an object. So object is a class that is at the top of each hierarchy. All right. Now in Python, every object has an identity, a type, and a value. So if I have this object, to get its identity, you can use the id function, which returns an integer telling you the identity of the object. In the CPython interpreter, it's the memory location where the object is put, but this can be different in other interpreters. So it's best to treat it just like an opaque number. And if you have two lists, you can find if they are identical by using the is operator. So A is B returns false. But if I alias A through B, then A is B. So ID of A will be identical to the ID of B. So that's the identity. Then there is type. We can find the type by calling type. So type of A is list, type of 1 is an integer, type of this is dictionary. So every object also has a type. And first the value. So for example, the value of X is now 2, and the value of A is the empty list. It depends on your object what its value is. But generally speaking, every object in Python has an identity, type, and value. Objects in Python do not generally have a fixed layout, contrary to other languages. So for example, you can create an object. We can create an object. So let's define a class, just an empty class. Let's instantiate it. And we can add attributes to that object, X, Y, Z, and then access them. So even though we haven't declared them anywhere in the class, we can add them even after instantiation. We can even add new methods to classes. So for example, we can create a new method on the class by using a lambda function. And if we now call foo, we will get 5. So you can change pretty much everything with some exceptions, which can be sometimes useful as you can dynamically add new attributes, methods, and so on. The exception is some built-in types like int. So for example, you cannot add a new attribute to the built-in class int or other built-in classes. Which is nice. Now for construction and so-called finalization, let me open a text file and prepare a class. Let's initialize it with an attribute, and let's create an instance of A. Now let's run it. So we have the X object here. So this is what you are probably used to. So you have an init function which is used to initialize the object. And if I print here debug print and I run it, it prints a dot init. However, that's not the whole story. There is another function which is called new, and this function is executed before init, and that's the function that is actually responsible for creating a new instance of the class. So we can also print it here, new. As we are unable to create our own instances, we have to delegate the work to the base class, which is object. So let's call new here. And if we run that, it will print a.new and then a.init. So this creates a new instance, and this initialize the instance. If you take a look at the Python's documentation, this is called a constructor expression, and these are just the two parts of the constructor. So this creates a new instance, and this initializes the instance. Now you may ask, when would I need to override new? And I know about only a single case where I had to do that, or when you need to do that, and that's when subclassing built-in types. So if we want to create our own string, which inherits from str, we cannot use init to initialize the string. For example, if we want to strip it before storing, as the string is already initialized here and strings are immutable in Python. So we need to override new. This will be our string. So what we want to strip it, and then we will call new my string, or can we just use class and as to return the string. So we can create our string in this way, something, yeah, let's do that. If you run it, we have our string, and as we can see, it was stripped in here. So that's one case where you need to override new instead of init when subclassing immutable types. Also, what might confuse you is that this takes a class, yet there is no decorator. That's a special case in Python. New is automatically a static method. It's not a class method. There are technical details which I don't want to go into right now. So it's a static method, implicit static method, and its first argument is a class. So this is why you don't have to decorate it, and it will automatically behave as a static class. But for all common purposes, you can treat it like a class method, but it's actually a static method. Now we have seen how construction works, and let's take a look at destruction. So let's go back to our example. Yes, this one. So this we have seen. It is possible for you to write a custom so-called finalizer called del, which is called when the instance is being garbage collected. So for example, if we have x and we delete x and run the program, it will also print a.del. But this is just because we use CPython, which uses reference counting as its underlying garbage collection method. And so the object is garbage collected as soon as its reference count reaches 0. But if we run the code in PyPy, we will just see a.new and a.init, as PyPy has a full-fledged garbage collector, which does not guarantee that immediate deletion when reference count reaches 0. So bear in mind that this method is only count when the object is garbage collected, which happens when after its reference count reaches 0. So if you have several references to an object and you delete a bunch of them and you have a reference which is still available, del won't be called. And also you cannot, Python doesn't guarantee that the del method is called for objects which are in existence when the interpreter exits, which is why we haven't seen the call here when we ran it through PyPy, as Python doesn't guarantee that. So it is useful to close open file descriptors or open network connections like database connections, but it should be used as a last resort. You should always close your connections or file objects explicitly. And as for the terminology, this is called finalizer in Python, also in Python's documentation. It's not a destructor per se, like we have in C++ or in Rust. Because of that, undeterministic behavior regarding the time when the method is actually invoked. So it's called a finalizer, just like we have, for example, in Java. And it's a dunder-del method. Next topic is multiple inheritance and MRO. So let's clear things out. I have prepared an example ahead of time, so I don't have to go and write all these classes. It's the classical diamond hierarchy. So A is at the top, then B and C inherits from A, and then we have D, which inherits from B and C. This shows us that Python supports multiple inheritance, just like C++, which is nice. It allows you, there are less limitations than, for example, we have in Java, which only supports single inheritance, but classes can implement several interfaces. In Python, we can use mixins, several base classes. If you need that, you can use that. So let's create an object, like let's create D, and let's experiment, not test, but multiple inheritance. So we have D. Bear in mind that this bar is different from these foos. So let's call d.foo, and if we call it, we see that Python called the implementation from B. If this were C++, you would get a compiler error, as foo is implemented by both C and B, and the compiler would shout at you that you have an ambiguity and he is unable to resolve it. So you would have to resolve it manually. But in Python, the method that is actually called is deterministically defined, and it's defined by this MRO list, which all classes have. Basically, what happens if you create a class or a class hierarchy, Python will go over the class and the hierarchy and construct this MRO list for you. It will use a so-called C3 linearization algorithm to do that. So no matter how nested or how branchy hierarchy you have, Python will be able to linearize it into a list or a tuple in this case. And this MRO list tells Python how to resolve attributes and methods. It is called MRO from method resolution order. However, it is also used when resolving attributes, not just methods. So first we can see that Python would use D or look for an attribute in D, then in B, C, A, and finally in object, which is the base class of every class hierarchy. If we call bar, then as only D implements bar, it's called in D. In Python, by the way, you can even create your own MRO list. So it's possible to, if you dislike the used algorithm, you can create your own algorithm. For example, you can use depth first search or order the classes by name or whatever floats your boat. But by default, what you get is probably something that you would expect. So for example, Python starts looking at the class itself, then it goes through the left to the right when looking for base classes. So for example, it will first go through B and then through C, and so on. So it's just like you would probably expect. Let's get back to our slides and discuss methods versus functions. So if I open the basics module, we have a circle here. So let's run it. We have a bunch of circles. Doesn't matter, C1 and C2. And if we take a look at that area method, Python prints that it is a so-called bound method, circle area of our circle object. If we take a look at that area in the class or through the class, it's just a regular function like you would create yourself. Right? If you take a look here, it's just, it looks like an ordinary function, and actually it is an ordinary function. But if you access it through an instance, it will return something called the bound method. We will see how this happens and later. However, you can either get the area of C1 by calling its area method, or you can go through the method or the function in the class and just pass C1 as self. It does not really matter. The result is the same. So, what to take from that? If you access a method from an instance, you will get a so-called bound method. If you go through a function or through the class, you will get just a regular function. So let's continue. Python loves dictionaries. It uses them all the time to store data and objects. So let's run Python interpreter. Let's create a class. So we just do that and instantiate A, and we can see that A returns this one, or we can add another attribute there. Data are stored in this dictionary, which can be accessed either through another dict or via the wars function. It's an abbreviation of variables, and it tells us that the A object has two attributes, A and B. So whatever you put here, it will be put into that dictionary. Classes also have dictionaries. However, in their case, it's a so-called mapping proxy, as it's a dictionary that also looks into base classes. So if you search for something in that dictionary, it will go over dictionaries from base classes. And here you can see that, for example, we have that init function there, weakref, which is used when using weak references, and a docstring. Now, if you import a module, modules also have dictionaries or store their data in dictionaries. Or if you create a function, functions also have their dictionaries. So pretty much everything you have in Python has dictionaries, except for some cases like slots we will use later or see later. So that's about the underlying storage. Now let's take a look at slots. Let's create another class. Everything great starts with a class, well, at least in Java. Not in Python. In Python, you don't need to use classes all the time. But let's get back on track. Let's instantiate here our A class. So we can access A.A, AB, or create a new attribute C. And everything is stored in our dictionary. A dictionary in Python is pretty much a hash table. So any object that you have in Python has a hash table, which has two consequences. Attribute lookups are kind of slow, as you have to do a hash map or hash table lookup. And also memory, it's quite memory inefficient if all objects have a hash table. So what Python offers in these two situations is slots. You can say that instances of A will only ever have these two attributes. So if you run the code and access A, B, that works as usual. But if you try to put another attribute into the object, Python will yell at you that there is no attribute C, because we haven't mentioned it in the slots. So A also doesn't have that dictionary. So pretty much you lose the flexible layout of objects. And you can only ever store something into attributes which are defined here. Right. So the reasons for using slot is can be more memory efficient, as Python will allocate an array for these attributes and will not need a hash table. So every access into an attribute will go through an array instead of doing a hash table lookup. The second reason is, and that's the reason why slots were introduced, is it can be faster attribute access. As you only have to go through an array, you don't have to do a hash table lookup. So these are some reasons why you may want to use slots. However, if you decide to use them, bear in mind that there are some difficulties you may run into. For example, with inheritance. If you inherit from a class and do not define slots, then Python will automatically assume that you need a dynamic layout and will add a dictionary there. So all classes in the hierarchy needs to have slots defined, even if empty. And also, for example, if you need weak references and need your objects to be able to be target of weak references, you need to add weak ref into slots. But that's for another topic. So just bear in mind if you need to use weak references. Now you may ask, what happens when I access an attribute of an object? What happens is there is some heavy machinery behind attribute lookup. And I very like this blog post, which contains a useful diagram of what actually happens if you access a foobar attribute on an object. As it says, it calls getAttribute on the class, and the default implementation does all the heavy lifting that you see here. When the attribute doesn't exist, the default implementation raises attribute error of getAttr. I will not go through the entire diagram. It would take us quite some time to go over it. Just bear in mind that what you see here makes, for example, descriptors work, as we'll see in a minute. And if you dislike the default implementation, you can create your own implementation that does whatever you want to do. So basically, you can take everything that's here and do whatever you want with it, including just throwing it out and do your own implementation. But it's useful that this is documented in the Python description, in the Python documentation, although there is no such diagram. And so it's not magic, it's just harder to understand, but you can pretty much code everything which you see here in Python itself. Now let's take a look how we can hook into attribute access, getAttr and getAttribute. So let's begin with class again. Let's just use one attribute and let's create A in this way. So if we access A, we get 1, But if we access some not existing attribute, Python will raise attribute error that there is no such attribute in the object. What we can do, we can intercept that by defining getAttr, which takes the name of the attribute that we are trying to access. We will put here a debug statement, so we see that it got called, and we'll return our favorite number, for example. So now if we try to access A, nothing really happens. That's just as usual. But if we try to access a non-existing attribute, Python will call getAttr, and then this function will return 42. So whatever you try to get, you will always get 42. There is also setAttr, which allows you to intercept setting of attributes. I will not go and talk about it in this screencast, just bear in mind it is there in case you ever need that. The second piece of the puzzle is getAttribute, which intercepts all attribute accesses, all of them. So be careful when implementing this one, as you can easily get into infinite recursion if you are not careful. So what we will do, we will just log the access, and then we'll fall back to the default implementation. So if we reload, and if we now try to access A, we see that the A exists, but getAttribute was called. And if we try to get some non-existing attribute, getAttribute is called, then getAttr is called, and then 42 is called. In case you are wondering, there is no setAttribute, there is just getAttribute. And I'm not sure why this is called this way, getAttr and getAttribute. It seems to be historical reasons, but I don't know. If you do know, please let me know in the comments. I would like to know the reason, if there is any. I don't see why you would introduce two functions which are named pretty much in the same way, but anyway. So in this way you can intercept attribute access. So this one intercepts all attributes, this one intercepts attributes that do not exist in the object. Now the final part of this slide is descriptors. Descriptors are kind of an advanced topic in Python and can be seen as magical. I can see that, but there's not much magic behind them. It's just Python works this way and uses descriptors when using methods, properties, or static and class methods. I think the greatest punchline or the greatest description of descriptors that I saw or heard is that descriptors are reusable properties. So if you know properties, properties are also implemented via descriptors. Descriptors are described in the official Python documentation. You can take a look there. It describes something called the descriptor protocol, how you call descriptors. There is also an example, how you can implement properties in Python, how functions and methods work, and so on. I will just highlight a few things about descriptors, but if you would like to know more about them, I suggest reading this page or looking at a screencast that discusses descriptors. So let's see what they do and how they work. So we'll implement our own descriptor. We'll name it just my descriptor. What we need to implement is either of these three methods. It's get, its set. They are described here, object value, or delete, right? If you define one of these three functions, then your class is treated as a descriptor by Python. We will just take a look at get and disregard these two, so I will remove them. What we'll just do, we'll print that my descriptor get was called with self, instance, and owner. And this is all our descriptor is going to do. Well, we can return our favorite number from here to see that it was actually called. Now we defined our class, and as an attribute there, we'll use our descriptor. So now we will instantiate A and play with the code a bit. So now what happens if we access X? Python, or the default implementation that we saw here, will found that there is an attribute which has get, and it will call it here through this branch. So our X is a descriptor, it has get. So if we access X, instead of returning that descriptor, Python will call get here. So we see that get was called. The self is an instance of the descriptor. Then as an instance, it's the object from which we have accessed the descriptor, and class, or the owner, is the class of the object through which we accessed the descriptor. So when we accessed it, we see that our get got called and it returned for 42. So this is the main idea behind how descriptors work. So instead of returning just the attribute, it will call a method which will then compute this attribute and return a value to you. So descriptors can be used, like I said, as reusable properties. So for example, if you have a class person, you can have age, and you can right, let's do it this way, like age, which will return your age. Or we can return, for example, I don't know, favorite number, right? And you can have all sorts of these properties, and we can, for example, return self age right here. Then we can define the setter for self new age, and here we can put a check. So for example, if new age is less than 0, we will raise value error with something, right? That I don't know, new age has to be positive, right? And we would do the same, we would put the same check into favorite number and so on, which gets tedious quite easily if you have a lot of properties. So what you can do instead is define a non-negative descriptor, non-negative, and use it in this way of favorite number. So you don't have to duplicate your checks, for example, for non-negativity and so on. So that's the basic gist behind descriptors. Now let's see how methods are implemented by using descriptors. So let's implement a class that does a very silly thing like returning 42 by calling foo. So if we instantiate a, we can call foo, right, and it will print 42. So if you run it, we get 42. And as we saw, if we access foo this way, it's a so-called bound method, a foo. So now we will implement that without using methods. So what we will do, we will define our foo function here, like here, return 42. And here we are going to define our function foo as an attribute, right? And it is going to be our own class, which is going to be a descriptor, as functions are descriptors, as we'll see. So we will need an init function in which we will store our function, and then we will need get to do the magic. I will explain this in a moment. So disregard this for the moment, I will describe it later. What now we want to do is that if someone accesses foo by the instance, we want to create that bound method. What we can do, we can use functools partial and apply instance to function to assign self or assign the instance to self. So we will need to import functools, and what we will do, we'll take our function, bind instance to self, and just return it. Yeah, so self function, right. This is strange. Method has no attribute function. Self function, we get function here. Why doesn't it work? So let's do some debugging. We put foo here. It should be stored as the function. Right. It should be called. Method. This should be called with foo. Well, that's the danger of live demos. So bear with me for a bit. Why is it not calling init? Alright, sorry for the pause. I didn't want to get you waiting. I also had to take off clothes from my washing machine. Anyway, I forgot to assign function. Silly error. Well, what you do? So now if we load the module, we can call foo, and what it will do, it will invoke our descriptor that will bind instance to function to self, and then we will call it. So here, if we access a.foo, we see that it's the partial application of the function. Now, previously we saw that it was a bound method. We can fix that by, instead of using functools partial, using method type from the types module. So if we run it again and access a.foo, it prints that it is a bound method foo, like you would expect. So, but the method type works basically the same. It binds instance to the first parameter of the function. So we can call it, and it works. Now let me describe the reason behind this code. If we access foo this way, Python calls get with no instance. As there is no instance, there's just the class. And so if we see that there is no instance, we just return the method itself. In this case, we can either return function self, right? A foo, so it's a proper function. Or if we decided to return self, we would had to implement call, right? Args, qargs, and then call the function like this. So there are multiple options which we can employ, but that's not really important. So here we saw that we were able to implement methods by using a wrapper class, just by using descriptors. Well, this whole code is unnecessary because functions are actually descriptors by themselves. So if we get that, we can access a foo, and we see that it has a get method. So if you create a function, it is automatically a descriptor, which behaves in the way we have just implemented. So if you access it through the class, it will just tell you or return the function itself. But if you access it through an instance, it will create that method type, which describes itself as a bound method. So there is nothing magical to methods. It is just that functions are descriptors, and if you include a function into a class, then this part will call the get function on the descriptor and return the result. So this is the reason why it is there. In case you were wondering, this branch is called for so-called data descriptors, which have either set or delete or both of them, and they also can have get. If we have a non-data descriptor like function, then we go to this branch. All right, so I think that's all for descriptors. All right, let's move to the final part, which is the most juicy one, and that's about metaprogramming and metaclasses in Python. So first of all, what is metaprogramming? Usually when you write code, you write something that does what you need. So it performs the action that you want. In metaprogramming, you write code that manipulates code that does something. So there is an extra level of indirection. So basically that code that manipulates code. For example, reads code, generates code, analyzes code. That's metaprogramming. One thing to note is that classes are instances of so-called metaclasses. So if we get back here, we have that, or we saw that if you have a class, then you can create an instance. So instantiate a class. In Python and in some other classes, in some other languages, what you have is a meta class that by instantiating a meta class, you create a class, and then by instantiating a class, you create an instance. So a class can be seen an instance of a meta class. These meta classes are in several other languages, for example in Ruby or Smalltalk. And if I'm not mistaken, meta classes could be in C++ 23, but it's only 2020, so we'll see whether they will land in C++ 23 or not. So there are some languages which provide meta classes, and it's an extra level of indirection. Now, when might you want to use a meta class? There are several cases. For example, you may want to register all subclasses. For example, if you implement the plugin system, you would like to be notified when someone subclass is your class to automatically register it somewhere. Or you may want to initialize attributes of a class, for example, descriptors, and tell each descriptor its name. We will also see how they do this differently at the end of the screencast. Or, speaking more broadly, you may want to modify a class before it is instantiated or after it is instantiated. Or you can verify subclass implementation like ABC, like the ABC package does, or ABC module in Python does. So there are many use cases when you want to use meta classes. I doubt that you will want to use one in all the projects. It's very handy in libraries, and you can create very nice APIs by using meta classes. For example, Django uses them, or SQL Alchemy uses meta classes. And I would personally use meta classes mainly in these cases to make the API of my library easier to use. In Python, the default meta class is type. So if you write, if we run an interpreter, type is the default meta class that we have. We also saw that type can be used to determine a type. It's unfortunate, but type in Python can be used either as a function-like object that returns the type of another object, or as a meta class. But type in Python is just a class. It's a class, but it's a meta class in a way that it creates classes. There are also other standard meta classes, like for example ABC meta, ABC meta, ABC meta, yeah, that's this one. Or if you use enum in Python, there is also a meta class for enum meta class. But the standard meta class that you will probably use is, if you define your own meta class, is type. So let's take a look at an example before going into the nitty-gritty details. I saw this example in a video by David Beasley, and I thought it was funny, and so I would like to present it to you guys. So let's say that you really like Java and would like to bring the Java's single inheritance model into Python for whatever reason. So we may want to define or ensure that all of our classes use only single inheritance. So what we will do, we will create our own metaclass called Java. We will inherit from a type. And what we need to do is we need to define new, which is used to instantiate a class. It accepts for arguments class, which will be the class that we are instantiating. That will be the meta class. CLS will be the meta class. Then name will be the name of the class that we are creating. Basis will be a tuple of base classes of the class. And dict will be a dictionary containing items in the classes dictionary that we want to put in there. What we want to do is we want to check if the number of bases is greater than 1, and if so, we will raise a type error no. And otherwise, we will just delegate the creation of the class to type, which will create the class for us. Now let's create a base class. If you want to specify a custom meta class, you do it by using the meta class keyword. So in our example, we defined a custom meta class. If you do that, you no longer need to write down an explicit meta class of your subclasses, because meta classes propagate through class hierarchies. So now we can create our class A, our class B, and if we run the code, it will work just fine, right? There's only single inheritance. But if we try to inherit from both A and B together, we'll just receive type error no. When creating the class, so it is this statement that produces the exception. So the class is not created as we have raised an exception from new. So in this way, you can manipulate or ensure that various preconditions hold when creating classes. For example, you might check that all methods are named in snake case, or that methods do not have more than, let's say, 10 arguments, or whatever you wish, basically. So that's the gist behind meta classes. You can also create a class manually. You do not necessarily need to use the class statement. So we'll take a look. Here we can define a class, let's say with a foo method that returns our favorite number. And that's all. Now we'll see how to create this class without using the class statement. So what we will use is the type meta class. The first argument is going to be the name of the class. Then we'll have a tuple of base classes, which is just object. And then we will need to have a dictionary. In the dictionary, we want to have a method foo. So this is going to be a lambda function that will just return 42. Bam, and we have a class. It's a similar class as this one. So we can instantiate the class and we can call foo, right? Foo is just a function. There are some differences, however, because the class statement is not just a syntactic sugar over this type, it does some more actions that are not seen. For example, it automatically sets a docstring for your class. It calls a dunder prepare method it calls a prepare method to prepare the dictionary for the class or it sets a proper wall name on the class, and so on. So the class statement does many more actions than just our type. But if you don't care about them, you can just use type like we did to dynamically create a class. Now something interesting, and that's the relationship between the type meta class and the object class, which we saw is the base class of all classes. We saw that object was the base class of all other classes. If we look at the basis of object, it doesn't have any base classes, it's just object. If we take a look at object, at the type of object, we see that object was created from type. Similarly as, for example, integer or a dictionary, all of them were created from the type meta class. So we see that object was made from type, but type inherits from object, which is kind of a chicken and egg problem, right? Object was created from type, by type needs object to be its base class. And that's one thing that is magical in Python. You cannot create this in the language. It has to be hard-coded in the interpreter. And if you take a look at the type of type, it's just type. So there's a loop there. So type is just hard-coded to be created from type. So we don't have to need to have meta classes and meta classes and so on. Now, what actually happens when you create an instantiated class? We'll take a look at the dunder methods that are employed when creating classes and when instantiating them. So what we will create will be our own meta class named just meta. And we'll create a class that will have a meta as its meta class. So if you run it, nothing happens as we don't have any print statements or calls or something. But meta was used to create A. So if we'll take a look at the type of A, we see that it's meta. It's not type, it's meta. The first thing that is called, as we saw, is new, which receives the following parameters. Let's put a print statement here to see that new is called. And let's just use the base implementation to create the actual class. So now if we run it, names. If we run it, we see that when creating the class, Python called meta new, which created the class and then bound it to uppercase A. There is also init, which is called after new. We can put a print statement in here to see that it is called. It's I can't think of an example where I would overwrite init or write my own init. Usually new is just enough. But if you need, you can just overwrite init and put whatever you need there. Then of course, or generally, you should also call the super implementation of init in case you have some shenanigans in the base meta class, or you have a more nested hierarchy. So if we run our code, we see that new was called when a class was instantiated and the class was put into the init method, which could then do whatever it needs. In our case, it doesn't do anything except of printing and calling the base init. So that's what happens when you create a class. Now let's go a level deeper and see what happens when you actually instantiate the class, like here. So we saw that there's a new function here, which is called to create an instance of the class, and we'll just delegate it to our base class, which is object like that. So if we run the code, it additionally prints a new. Then of course there is init, which initializes the instance. So let's also print a debug statement here, run it, and we see the complete sequence. However, there is one more method that is employed apart from prepare, but I'm not going to describe prepare. If you take a look, it resembles a function call, right? If we had a foo here, it would be just a function call. So in this case, we are actually calling the class, and you can override the behavior or make your objects callable by defining call, right? However, you need to, if we want this to work, we need to define call in the meta class. Otherwise, if we defined it here, only objects or instances of A would be callable. So we would be able to call our objects. But if we want our classes to be callable, we have to go one level above, which is in the meta class. So we can just call meta call and delegate it to the base meta class, like that. So if we run the code, it will additionally print meta call, right? When in this line. So it's meta call or meta new, then it's meta init. Then when we instantiate the class, it's meta call, then it's on the class new, and that is init. So that's almost the whole story of what happens when you instantiate a class. We can also see what happens when we access an attribute of a class, just like we did for objects. So if you take a look at my favorite blog post by Yonel here, there is another diagram which describes what happens if you access an attribute on a class. So instead of calling getAttribute on a class, it calls getAttribute on a meta class, which also has a default implementation. There is also getAtter. The diagram looks slightly different because we need to also employ handling of descriptors. So this is why this branch is new here. It wasn't here. It's just returning an instance from the dictionary. But here we have a more complex handling. Anyway, this is described in the Python's documentation or in the blog post. So if you need to see exactly what happens, take a look here. or just redefine get attribute in the meta class, and you can implement whatever your heart desires. Now, you don't always need to use meta classes. Python has several features that you can use instead of meta classes, and which can be easier to use in some particular cases. So let's take a look at them. The first one are class decorators. So let's clean that up. You have already seen this syntax when using functions, right? It's a function decorator. We can also write class decorators, which accept classes as their inputs, do some magic with them, like adding new attributes, checking that something holds, some preconditions hold, and so on. So you can create your own decorator on a class. The downside is that if you have several classes, like class B, which inherits from A, you also need to apply a decorator on class B if you want it to be applied, as decorators do not propagate through hierarchies, in contrast to meta classes, which do. So that's one downside of decorators. But they can sometimes be easier to write and easier to reason, or easier to read for people who haven't encountered meta classes. So that's one thing you can consider, is using decorators. Now, from Python 3.6, we have this special method in its subclass, which is called on the base class whenever someone's actually subclasses your class. So let's have an example. It's useful, for example, when implementing plugin systems. So for example, we can have a list of registered plugins, and then we can define it subclass, which is implicitly a class method, so we don't have to define it as such or decorate it as such. And what we will do, we will just append the class into the list of registered plugins. So if we implement plugin 1, which inherits from plugin, then we can implement plugin 2. And after that, we will print the list of registered classes, and we see that it was automatically populated with plugin 1 and plugin 2. Because when you subclass the class, in its subclass is automatically called. So if you just want to have a plugin system, there's no need for meta classes, you can just use init subclass. SetName, that's also available since Python 3.6, and that's used on that's used on descriptors. Because sometimes you may want your descriptors to be able to know into which attributes they were assigned. So, for example, if you have my descriptor class, which we will implement later, and you have a class A, and you want to use my descriptors like that, BC. So you may want to let the descriptor know that in this case it's assigned to a variable A, then to variable E, and then to variable C. In the past, what people usually did was duplicate the name of the attribute here, but that's error prone and leads to duplicated code. We can do better. Right here I made an error, just like that, you know. So we can do better, and we can do better by using setName. So if we define setName then we'll accept these arguments, and let's just print whatever we have. So let's print self, owner, and name. And if we run the example, we see that in the name parameter, we get the name of the attribute into which the class was assigned. So it's A, B, and C. So that's useful when using descriptors, so you know into which attribute the descriptor was assigned. And last, but certainly not least, you can employ code generation. You can create code in a string by appending, by modifying the string, and so on. And after that, you can call exec, which will execute your code like that. So if you know, for example, 1 + 1, and if you execute it, it will print you. So you can create your own code, execute it, and create classes or whatever you need by manipulating strings. This is used, for example, in the implementation of collections named tuple by Raymond Hettinger. And you can also use it in your code if you wish. So that's pretty much all. What is left is for me to go through recommended reading and watching. So first of all, there is Python documentation on the data model, which describes in greater detail what I have just told you. You know, here you can see new, del, other special methods, customizing attribute access by getAuthor. Here are descriptors, how to invoke them, slots, customizing class creation, metaclasses, Amaro. So if you want to need the nitty-gritty details, I recommend reading this reference page on the Python's data model. Then we have the description of descriptors and Python's documentation containing many examples. Then there is the description of standard types in Python. There are several of them. We saw method type, but there is also, for example, code type for code objects, function type for functions, and other types. I can also recommend this blog post by Evie, which describes object models of various languages like Python, JavaScript, Ruby. It's very nicely written and I can recommend that. Then there's the blog post by Jonel. I highly recommended it. It's good reading with many examples and diagrams. There's a presentation of Python object model that you can look at also. Then there's a Stack Overflow page on the usage of slots, which contains a description of what I have told you, again in a greater detail. And then there are two videos. The first one by Dave Beasley on Python 3 metaprogramming. It's 3 hours long, but I really liked it, so I would highly recommend it. So you know more about Python 3 metaprogramming. And then there's a presentation by Mark Smith on PyCon, which is 1 hour long, and I also enjoyed it. And it contains several great explanations of various concepts in Python. So that's all for me today. If you have any questions or suggestions towards the videos, please let me know by writing a comment. And see you later some next time. Bye.